Okay, what's up, guys? Okay, what's up, guys? Okay, what's up, guys? Let me double check. Yeah, that's looking good. Okay, we actually have someone here? Oh, how about that? Cool. I kind of figured maybe no one would show up since it's almost spring break. All right. Well, all right. So today we are doing a bonus math. I just figured out how to do like the soundboard thing. I'm very excited about that. It's pretty cool. This is going to greatly enhance the quality of our lectures. All right, so today we're going to talk a little bit about the maximum modulus theorem and harmonic functions. So this is all bonus math. This is all just not on the exam. It's not going to be a homework, anything like that. This is just one quick kind of overview, short lecture to sort of answer a question that we asked a little bit earlier in the class. In particular, when we talked about harmonic functions, we raised a question. So we found out that a holomorphic function, an analytic function, a complex differentiable function satisfying the Cauchy-Riemann equations, has real and complex parts that are harmonic, and they come in a conjugate. They're harmonic conjugates of each other. And so it was a natural thing to ask, okay, given a harmonic function, when is it the real or imaginary part of a analytic function? So just asking the reverse question, kind of a classic thing to do in mathematics. Say, okay, I've got a thing. I know that A gives you B, but when does B give you A? And that's a great question to ask, because if you can determine, the both answers to the questions, you can kind of determine how the two things are different. And that motivates a lot of what is done in mathematics, just broadly speaking. People trying to figure out what is different between various things, just in terms of converse implications. So how we're going to start this out is by a basic observation. The observation that we're going to make is the so-called mean value property, and we've kind of alluded to this before when we say that a analytic function its value at a point is determined by its values on curves surrounding that point, provided that point is nice with respect to its domain of analyticity and the curves are appropriate given those various constraints. This is the content of Cauchy's integral formula. So one way to maybe say this a little bit more precisely by picking a specific curve would be to grab a circle of radius, say r, about a given point. And we can just directly compute using Cauchy's integral formula and find that f of z naught is 1 over 2 pi times the integral from 0 to 2 pi of f of z naught plus r e to the I theta d theta. Okay, so that just means integrate the function around the circle of radius r centered at z naught. Okay. Sorry, I just realized I'm still wearing my headphones and hearing myself talk is throwing me off. Okay, that's a lot better. So anyway, so just integrate the function around the circle of radius r centered at z naught. Kind of nice. So we can prove this. The result more specifically states that if f is analytic inside and on a circle of radius r centered at z naught, then we get this result. But that's just the exact context of Cauchy's integral formula. So by Cauchy's integral formula, we immediately get that f of z naught is 1 over 2 pi I times the integral around any closed curve containing z naught on and in which f is analytic, of f of z over z minus z naught. Okay, just Cauchy's integral formula is what we've been dealing with. Cool. Now, if we take gamma to be the curve, gamma of theta is z naught plus r e to the I theta, then we can just actually plug everything in. throw in gamma in the bottom here for z, so z naught plus r e to the I theta. Oh, look, that z naught and this z naught here cancel each other out, so we just end up with r e to the I theta down there. Then when we take a derivative, we get I r e to the I theta. Look, the I here and the I here cancel out. We've got an r e to the I theta and r e to the I theta there. And hey, we just get 1 over 2 pi integral from 0 to 2 pi of f of z naught plus r e to the I theta. Since 1 over 2 pi is just 1 over the, what? Well, so, okay, so what is pi again, right? It's the ratio of the circumference to the diameter, right? And so this is, in essence, it's just like a normalizing factor. It's kind of like the mean value theorem from Calculus 1. But the more crazy part is that it doesn't just hold for some point, it's for every point. It's this sort of, it kind of gives you the sense of why we call it the mean value property. It's this analog to the mean value theorem that is so much stronger than the regular Calc 1 mean value theorem because it holds at every single point, not just for some point and any given curve. It's kind of crazy. So this starting place will give us, it tells us basically that an analytic function at the center of a circle is its average value around that circle. That's the way to say it. And this idea lets us prove the maximum modulus principle. This fact is instrumental in it. So the maximum modulus principle in its most basic form that we're going to start with. So the local version of the maximum modulus principle says that if you've got an analytic function f on a region A, and this is the messiest highlight, and f in modulus has a relative minimum at some point in A, that is, f of z is in modulus less than f of z naught for all z in some neighborhood of z naught. So everything nearby in modulus is smaller, or at least not bigger, right? So a relative maximum, right, where everything is smaller nearby, just like in Calc 1. Then f is constant in some neighborhood of z naught. A good way to think of this is that you can't actually get things like the Calc 1 picture of a maximum, like right here, right? We don't get that. That does not happen in complex world in a certain sense. None of that business. Just not happening. Not in the world of analytic functions. The only things that do this are constants. It's kind of got the same sort of flavor as a result like Liouville's theorem, where a bounded entire function is constant. That is kind of, if you think about it, basically the local version of Liouville's theorem, if you want to say it like that. That is, if you imagine, you got some point here, z naught, at which you achieve a maximum, then you're saying, okay, we'll just grab a small disk around it, right? Don't include the points on the boundary of the disk. And really, isn't this kind of like the whole complex plane anyway? At least basically up to a homeomorphism it is, right? Just imagine stretching this disk out like further and further and further and further, right? You could map everything in a little disk to the entire complex plane. And so Liouville's theorem sort of says, hey, if this is the biggest you get, then, well, got to be constant, right? Since everything is in the domain of analyticity, right? Analytic on a region A with z naught in A. Remember, a region is an open set, so we have to have a little open set about z naught that is completely contained within A. So we can always do this. That is, A is always something bigger, where you can take the z naught and always get something around it. So in this little area, basically, and this is the intuition I think that is most useful. Think of this as just Liouville's theorem again, but carried through stretching out a little neighborhood into the entire complex plane. It's kind of like saying, if that seems weird at all, it's sort of like saying that if you look at all of the points between 0 and 1 without including 0 or 1, it's basically the same in some sort of a sense as looking at all of the points between negative infinity and infinity, right? Because you never, no matter how far you go, you never get really any closer to the endpoints because you can always keep going further, right? So it's the same kind of a thing, except with like a disk, an open disk now instead of an open interval. This is basically like the complex plane. So the kinds of things that hold for the entire complex plane, like Liouville's theorem, should carry through. That is, if you're bounded, then you should have to be constant, provided you're analytic. So this is the local version of the maximum modulus principle. You can imagine as well that there's a global version, and it would basically kind of be the same sort of thing, right? So to talk about this a little bit more precisely, we'll need to talk briefly, at least, about closures and boundaries. So intuitively, think about it like this. Intuitively, if you've got, say, like a disk, right? Let's say that you've got a, I'm going to try to make this real. So here's your disk. Sorry, I'm not trying to make it like swirly or whatever. I'm just trying to shade it in. So here's your disk. Let's call this disk, I don't know, let's call this disk D. What you've got is that this edge is the boundary. Inside is the interior plus boundary is the closure. So you can kind of think of it like that. And just this is sort of the picture you want. If you had everything here except for the boundary, you could close it, which means just adding in the boundary. And what we're trying to say more formally here, I'll say it in formal terms, but just think of the disk, and it's like the easiest kind of example to adapt it from. What our definitions are formally, so definition 2.5.3, the closure of a set A contained in the complex plane, though you can also do this for any topological space if you want. Well, provided that it's, I shouldn't say for, yeah, you can do it. You can do it for, okay, yeah, I don't want to introduce any more confusing concepts. Think of it like this. The closure of a set in a topological space is the smallest closed set containing that set. So a closed set's closure is itself. A closed set of the closure of a non-closed set is the smallest closed set that contains that set. This always exists because the whole space is always, both open and closed. So you can always find the closure of some set. It might potentially be the whole space. So, and if you take the closure of the empty set, it is going to be the empty set because that's also open and closed. So the closure of a set A, particularly in this case contained in the complex plane, though you could really do this for any topological space, which you generally denote by A with a little bar on the top of it, close it, or by CLA, closure of A. This consists of A together with its limit points. This works when you have some notion of unique limits. You can, in particular, this works with Hausdorff spaces. We don't need to talk too much about it. You can do it when you don't have unique limits as well. We don't need to care about that right now. It's just A with all of its limit points, so you just take every convergent sequence of points in A and you add what it converges to. So if you had the disk without the boundary, you could grab some points in there that get eventually very close to the boundary, and so you'd end up with some point on the boundary, right? And since you could do this for any other set of points going to the boundary, you'd eventually get everything on the boundary, right? Okay, fair enough. If you just had some of the points on the boundary already there, then okay, you don't have to add those ones. The boundary then of a set A in the complex plane, once again, you could do this in any topological space. We generally write this BD of A, or the boundary, or some people will write partial A, del, I don't know why, boundary of A. This is just the closure of A intersected with the closure of the entire space without A. So the closure of A intersected with the closure of the entire complex plane sans A. And this gives you the boundary. That is, if you looked at everything that converges to something in D, and then you look at everything here that goes to it from the outside, right? The union of those two things will give you that edge. You know what I'm saying? So just think of a circle, or even just think of like an open interval. Say you've got an open interval A, then the closure of A will of course be the closed interval from 0 to 1, and the boundary of A is just going to be the set 0, 1. See what I'm saying? So the boundary is the edges and all that, right? If in this case you're looking at D, the boundary is the boundary of the circle. It's exactly what you intuitively expect. Okay, so talking about boundaries and closures makes certain statements we're going to make a lot easier. In particular, the maximum modulus principle in general. So if we have A, I'm going to get a highlighter out. This is the maximum modulus principle, the non-local version. So if you have A, an open set, connected, bounded in the complex plane, and F, a function from the closure of A into the complex plane that's analytic on A and continuous on its closure. So that means, analyticity obviously gives you continuity on A, but continuous on its closure means that it's also continuous on the boundary, right? So continuous on the closure is important. Then modulus, or F in modulus, in absolute value right there, right, has a finite maximum value on closure of A, which is attained at some point on the boundary of A. So this is kind of cool. It says that the maximum modulus that an analytic function on a closed set can obtain is on the boundary of A, and it always attains its maximum on the boundary. There always is a maximum. If it's also attained in the interior of A, then it's constant on the closure. So this is kind of the nice difference if you want to think about this between Liouville's theorem and this result. So the previous local version, like I was trying to say, is, and hopefully it makes sense, is basically just Liouville's theorem all over again, passed through like a bending of an open set into the whole space, right? A continuous deformation. You can take a disk of radius r and, make that r bigger and bigger and bigger or something, right? So you can stretch it on out, right? Okay. So the deal with this is that you get an extra piece. You just had Liouville's theorem before, basically, and this end piece basically is Liouville's theorem yet again. But the nice extra part that the maximum modulus principle provides us is that F does indeed have a finite maximum value in modulus, and it attains this at some point on the boundary of the set. Okay, so that's kind of cool. That's kind of neat. Basically, it means that you get your holomorphic function, or your analytic function, is always getting bigger in modulus unless it's constant. If you go to think about like, okay, you've got some disk, your function f may be changed its maximum right here. Okay, well then grab a bigger disk now. That cannot stay the maximum because otherwise, well, it would have a maximum on the interior, right? If this function is non-constant, and that would contradict this. So it has to obtain attain a different maximum, maybe like over there on the boundary of this bigger set. See what I'm saying? It's always getting bigger. Oh, that's nuts. It's kind of cool. This should guide your intuition with certain yeah, there's some true false questions in the exam that this might help you with, just in case you want to double check your work, though it doesn't. You should know already, but you just apply Liouville's theorem to some of them, but this more so tells you that. This is kind of nice. So one thing that is worthwhile to notice is that, and here I'm going to actually kind of skip ahead a tiny bit. Well, here. We'll skip it for the moment. Yeah, we'll skip this for the moment. I was going to make an additional side. It'll be cleaner to get to a little bit later, so I'll keep going. I also don't want to drag this on forever. So, harmonic functions and harmonic conjugates. This brings us back to the kind of question we started with, this initial piece where we said, hey, we know that analyticity gives us harmonic functions, the real and imaginary parts of the analytic function, and we know that they come in conjugate pairs. Okay, cool. Now, what about the opposite? When I have a harmonic function, when is it the real or imaginary part of a analytic function, and given a harmonic conjugate pair of harmonic conjugates, a pair of them, when do they define an analytic function? So let's answer this question that I made a lot of ambiguous statements about a few weeks ago. Here. Okay, so let's answer this question now. We know that if f is analytic and f is u plus iv, we're going to keep using that notation, then of course u and v will be infinitely differentiable and harmonic. We already knew they were harmonic, but the infinite differentiability, of course, comes from this nice extension of Cauchy's theorem we got before, that integrals of Cauchy type are infinitely differentiable, and every you can write the derivative of an analytic function as an integral of Cauchy type. You can write an analytic function as an integral of Cauchy type, so all analytic functions are infinitely differentiable. Kind of nice. So of course, the real and complex parts of an analytic function must also be infinitely differentiable. And we already know they're harmonic. So the converse, as it turns out, is also true. Kind of neat. I was careful saying this earlier because it is not true on every set. In particular, you need to talk about a region A, and we need to be careful about a lot of details. So if we have a region in C and U a twice continuously differentiable harmonic function on A, then U is C infinity. Okay, we already know that now. Great. And in a neighborhood of each point, Z in A, U is the real part of some analytic function. If A is simply connected, there's an analytic function f on A such that U is the real part of f. Now, this is the nice kind of subtle distinction, and why in lectures past many weeks ago, I hesitated saying that the reverse is true, because these are subtle points, and that is kind of interesting to note that this can fail in these subtle ways. So it's not the case that U is just the real part of an analytic function on all the complex plane, or on even all of A in general. In fact, you only get a local version of it. It's just a neighborhood of each point. So it may be different analytic functions in different neighborhoods. Kind of crazy. And it's the real part of some analytic or it's there's just one function when we have simply connectedness. So if you don't have a simply connected domain, you may have different functions at different points, different analytic functions, and that is kind of cool. So it's not to say that you can always find a analytic function such that you get, every harmonic function as, a real part. Okay. You can find a function for each point where you can do that. So that's kind of a cool answer to the question. It's very localized, but it in a cool way says that really you're not constrained. You're maybe at most constrained on the domain, but thinking about this kind of like stretching out domains to like the whole plane or something like that, really, in some topological sense, you're not constrained at all. So it's kind of cool. Basically, it says the reverse is true up to a little bit of continuous deformation. And you have to be careful if you don't want to use that additional bit of bending. So a harmonic function is always the real part of an analytic function, at least locally. That is how lots of people will say that. Now, of course, everything we learned about analytic functions, we can carry through to properties of just harmonic functions. That is, we've learned something very interesting about twice continuously differentiable functions that have a zero Laplacian. It turns out that they're infinitely differentiable in if they're it turns out they're infinitely differentiable, and they have a lot of constraints on them. The same constraints we just saw for a holomorphic function, or an analytic function, since we're using that term. Uh, that is, we get, once again, the mean value property. So if U is harmonic on a region containing a circle of radius r around the point z naught, which we'll write as x naught plus I y naught in its interior, and in its interior, so on the circle, and there you go, on the inside of that, right? Then U of x naught y naught is just, this is exactly the same as before, what we were doing right over here at the beginning of it, the mean value property for an analytic function. That is, harmonic functions at a given point are also described in terms of their contour integral around a circle centered at that point. Their average value on that circle. Kind of cool. Okay, so the we also get a local maximum principle, analogously to the maximum modulus principle, except now we're not working in modulus. We're just working with actual maximums and minimums. So the local maximum principle for harmonic functions, okay, if you've got U harmonic on a region A, same setup as before. Now, if U has a relative maximum at some point in A, that is, if U of Z is less than or equal to U of Z naught for all Z near Z naught, same business as before, just no modulus bars, then U is constant in a neighborhood of Z naught. Okay, same business as before, but, now we're just dealing with a real function. Okay, cool. Of course, this makes sense. This has to happen, right? If this was not the case, then it feels like we would be somehow contradicting everything we've learned with the maximum modulus principle and all of that. That is, the maximum modulus principle just delivers these results to us so easy it's free. But we, of course, get the global version as well. So the global maximum principle for harmonic functions is kind of nice, in particular because we're working with functions that just go to the reals, take a pair of reals to a real number, right? Or take a complex number to a real number, right? Whether you want to think of the complex plane as ordered pairs of two real numbers with a nice additional multiplication on them. We can do something cool here. In particular, we can also get a minimum modulus principle, or minimum principle, which is kind of neat. So suppose that A is open, connected, and bounded. Okay, cool. We'll take U from the closure of A into R, continuous and harmonic on A, and we'll let M be the maximum of U on the boundary of A. Then U is less than or equal to M for all x, y, and A, and if U of x, y is equal to M for some x, y, and A, U is constant on A. So this is once again an immediate consequence of the maximum modulus principle, just because this is true for analytic functions, of course, because we can find an analytic function that agrees with, that has this as its real part in some neighborhood of a point, blah, blah, blah. We'll get this same business yet again. Okay. Open, connected, bounded. Nice, easy. Okay. So you can also do the minimum the minimum principle for a harmonic function. So we'll let little m denote the minimum of u on the boundary of A. Then in that case, u of xy is greater than or equal to m for all xy in A. And if u of xy equals m for some xy in A, then once again, u is constant, right? So you can obviously just get the minimum right away from applying the maximum principle to negative u. Easy, amazing. This is pretty cool, actually. Kind of returning to our picture before, we don't have this in the world of harmonic functions, but we also don't have the opposite version of it. In some sense, it says that everything in this case is kind of saddle shaped. So if you, I'm trying to make sure I can draw this picture well. I'm gonna do so bad at this. I'm gonna do the worst at this. Yeah, I'm doing such a bad job of drawing this. I can't draw this shape. Like it's shaped like a saddle. That is in one. Think of it like in one direction, it's increasing. One direction, it's decreasing kind of thing. This is sort of the. Let me see if I can get. Okay, let's see. Here's a random picture of kind of what I'm trying to describe. This is not exactly the right thing to think of, but basically like in some directions we're decreasing and some we're increasing, or we're constant, right? Otherwise we end up with a bad situation where we violated all of these principles we just described. That is, since you have to, if you have, say, like a given circle and we achieve, say, like our minimum here and like our maximum here, then we could just draw a bigger circle, maybe. I mean, assuming we can, right? And these can no longer be the maximums or the minimums unless we're constant, because we have to achieve it on the boundary. Oh, okay. So maybe like the minimum's there and the maximum's now here or something. It's not exactly like a saddle kind of shaped picture, but it means it has to be increasing in some sort of some direction, basically, and in some direction it's kind of decreasing. You can't have like biggest and smallest, so to speak. This is a very informal discussion of it, but you get the general principle. This is kind of cool. And what you end up being able to do with some of this is, in particular, if you end up taking like a statics class, is that this is very useful in constructing solutions to Dirichlet problems. So we won't talk about that too much because I said this would be a short class and it's already almost not a short class. But it comes up in physics. In particular, if you start with knowledge of a continuous function on the boundary of some set and you ask yourself, hey, when can I find a harmonic function that is equal to that continuous function on the boundary and harmonic on its interior? This is a classic kind of problem that comes up, say, if you're looking at like, lots of different things. An easy one is like the charge along the edges of something, or like the heat along the edges of something, or even if you're like looking at water, and you're just like, think about the ocean and just looking at the shoreline and how the waves crash up on it. Um, can we, from this information on how the waves hit the edges, can we find whatever the heck the function is on the inside? How can we construct that? And in some sense, what all these things about harmonic functions tell us, these mean value properties, max and min properties, all this stuff, it says that, hey, we can discern everything about nice enough harmonic functions from their behavior on the boundaries of things. So we should be able to do these things. And as it turns out, if you make nice assumptions and you set things up well, you can find unique solutions to Dirichlet problems. And so this stuff all comes back up in physics and engineering, and in particularly in statics. And you'll see a lot of good stuff. So if you are interested in this, I would recommend trying to take a harmonic analysis class at some point. I can recommend a textbook if anyone finds it an interesting topic, but I think that is a good enough introduction to a cool way that basically Liouville's theorem can be applied locally, and then a little bit extra can be gotten right out of Liouville's theorem, and some cool facts about harmonic functions come out that answer a question we posed kind of a long time ago in this class. So yeah. All right. I think that's probably a pretty good stopping place for this brief overview. And it hopefully is an interesting topic. I hope everyone has a wonderful spring break. If anyone has any trouble with the exam, please shoot me an email. I'll respond right away. And yeah, cool. Have a great Friday night.
Bruh.
All right.